Hello, everyone. Congratulations if you've seen all of my other talks. You made the right choice. So what I want to talk about today, it's my last talk, is memory efficient coding in the Wolfram language. So I want to show you basically how you can avoid some simple mistakes that a lot of people make when it comes to creating demonstrations and writing code, which ends up being more taxing than it should be. So it's kind of a hybrid between, I would say, memory efficient coding and CPU efficient coding as well. So it's not quite an accurate title, I would say, but I'm sure there'll be plenty of interesting stuff here for you. So the first command I want to show you is quit, because I'll be using quit a lot. Because what quit does is it quits the kernel. So what it means is if I say x equals 2, and I run x, and I now run quit, I run x again, and what I'll find is all the symbols have been destroyed because I've killed the kernel, which stores up all the symbols. You can also go to the top, in the top, I think you go to evaluation and quit kernel, and then you can select your kernel there. But in this case, we'll just use quit because it's faster. The second command is memory in use, which shows you how much memory is in use. So this is useful to know. So we'll quit the kernel again, even though we haven't really used up that much memory, and we'll find out what happens when we start with some. We get our start memory, and then we add some data. Store it into the kernel essentially and assign it to a variable data, a 1000 by 1000 grid, and we'll print out the difference. So what does this mean? How much memory is this data taking? And it's 8 million bytes. So okay, this is really good. So now we can go to memory in use, and before it was about 22 million, and now it's 30 million, as we would expect, the 8 million difference. And then now here's something which is quite interesting, and it's quite difficult to explain in some ways. So what you can see on the left-hand side is inputs and outputs. So it says in 3 here. Well, actually these ones aren't relevant, but when I ran the kernel, so if I run this, it says it's input 3 and output 3. So what that means is I can type in out 3, I think. It's just out 3, and I can get the result of the output. So all outputs are stored in the kernel. And this may be something that you're not aware of, that it actually does that. It stores the inputs as well, so I can go input 3, and it automatically evaluates. So I guess if I go hold input 3, it will, I can't do that, but I guess if I go down values in 3, or in fact, then we can find that in 3 goes to memory in use. So this is all very important, and one of the important things that I discovered was, let's say we just do random real, and we run it. Well, actually, let's do it a little bit makes more sense. So we get memory in use, we run random real, we find the memory in use, 8 million bytes, because it's stored in an output. Now, what you may think is if you now assign a variable to it, you're assigning a variable to random real, this 1000 by 1000 grid, and you've also got an output there as well. So you would expect, instead of an 8 million byte increase, you'd expect a 16 million byte increase. But this is just incorrect. So we run m equals random real, and we run it again, and we've got 8 million bytes more as opposed to 16. And what this means is if I now clear m, so I kill m, I get rid of the data there, and I run memory in use, it's exactly the same, or very close to exactly the same, because it fluctuates a bit. So this is very important to know, that your output, if you've got outputs like this, then your outputs will still be stored even if you assign the variable and you clear it and you think you're actually saving memory. So what you actually have to do is, you can clear out basically. So if you go to out, and I think this will be a bit messy right now. Oops. Down values out. This will show me all the values that exist for out with all the outputs. So it's going to take a while, so maybe I'll show you in instead, because I ran this way too many times. So down values in will be similar to down values out, but it will be the output for all of these things, essentially. So what you need to be aware of is that if you clear these values, so here I can say, let's go for, well, we can first of all, we can find the byte values for all of the down values on out, and we can see these 8 million ones are ones that have been assigned, and here we've got 32 million, which is a bigger memory usage. But what we can do is something that you shouldn't really do, but if you need to clear out, you can unprotect out and then clear it. So what unprotect does is it unprotects the symbol. So a lot of our symbols that exist, most of them in fact, are protected so that you can't make an assignment. So if I say out equals 2, oh dear, that's not good. Oh, it won't do anything. It shouldn't do anything. I think the error's coming up. Yeah, here it goes. It says symbol out is protected. But what I can do is I could unprotect it and then I could do it, but that would destroy everything. But what I can do is I can say unprotect out and then clear it. And now when I go to down values out, it's got no information other than the the output when it was cleared. So now if I run memory in use, I can see now it's reduced quite drastically. So this is a way that you can clear the output, and you can do it with the input as well. The input can do it in the very same way, but the input tends to not have as much data stored. We can remove a specific line, so a specific output by typing in unprotect again, and then going in this case, I guess I'll quit the kernel. I'll make some random real. Oops. And then I can do unset, which is this equals dot, and then it will specifically get rid of. It's 2. That's fine. It will specifically get rid of the output 2. So now if I do out 2. It won't have any value because I've done it. I've reset it. Percent line. So percent line is the output number that it's currently on. So if I run percent line now, it says it's on output 6. But if I say percent line equals 1, then I go to percent line and now it's 2 because it's I've now reset it to 1. So these are all cool things that you can be aware of. Second thing if you don't want to have to faff around with this, because this can be a pain, and you don't even care about your outputs ever, because you're always going to be assigning to variables, what you can do is change the history length. So the history length currently is defined as infinity. So what that means is that all the outputs are essentially stored. So now what I can do is I'll add some random reals again, increase the memory in use. I'll change history length to 0. And now I'll run this random real a few more times. And what we've seen is that the memory in use doesn't increase. But what you'll notice is the memory is bigger than maybe you would expect, because the down values for out have been stored. All of them remain stored before you define history length equals 0. So what you can do is you can define history length equals 0 straight away. Then run this command a few times, and now we go to memory in use, and we can see that it still remains at 22 million, which is what it was at the start. So we're actually saving on memory efficiency right here. So this is really useful to know. You can actually put it in your init.m file. So I don't know if you know about this, but it's a good thing to mention. If we go to $user-base directory, and we go to kernel, we have this file called init.m. And this is where we can define some initializations of some description. So what I could do is I could say $history length equals 0. And I'll just show that x equals 2 so that you can see that this works as well. So now what happens is I'll quit the kernel. And now I'll run history length. and it will say it's 0 because it runs the initialization init.m file first, and I'll run x, and it'll say x equals 2. So this is really, really useful, I think, for people. If they're doing the same thing over and over again at the start, and they want it to make sure that their Mathematica always runs something at the beginning, you can do this. Okay. Packed array, so special data types. So this is something which is really useful to know. So basically, there are some special array types, and one of them is packed array. And generally, you don't usually have to worry about it, at least the way that it's produced. So here we've got two tables of well, we got some random real numbers, 100,000 random reals, and 100,000 random integers. And then we can use this developer function, which you can access yourself, developer backtick packed array queue, to determine whether or not these things are packed arrays. And it says they are true. Now let's find out what the byte count of this packed array is. So one of them, real vec, which is the random real 100,000 random real numbers, 800,000 bytes. Now what happens if we append a integer value to a set of real numbers? So we've got 100,000 random real numbers, and then we've got one integer. What does that do to the byte count? Well, it triples the size, basically. And the reason for this is now you're mixing variable types. When if you want to maintain a packed array, they all have to be the same type. So what we can do is we can do another function, toPacked array, developer backtick toPacked array, where we append the value again, but we want to make sure the packed array is real. So it'll automatically convert all integers into real numbers. We get the byte count, and now it's 8 bytes. Which is great. Now, why a packed array is quite important, other than the fact that the byte count is lower? Well, they're more efficient to compute. So here we have total, which adds up all the numbers. So here we're adding a bunch of random real numbers together. How long does it take to do that? Or you can even give the answer. So we've got this function absolute timing, which tells us the time, 0.00037 seconds. And now we can actually, if for some reason we wanted to strip out the packed array and convert it into a normal matrix, we can do by using from packed array, and we can see that the time is reduced by 100 times to do the same calculation. Another type of array is a sparse array. So here we, if you have an array which is very sparse, so you've got a massive grid where numbers are basically all exactly the same except for a few values, you can use sparse array. And the byte count, well, in this sparse array, for example, is reduced by 7 times. And why is this important? Well, if you have a massive array, so here we've got a 1,000 by 1,000 matrix, and then we're of zeros, and then we're changing 400 of the values with random real numbers. How many bytes is it? 24 million bytes, it says here. Let's do it with a sparse array which is changing 400 of the sparse array values to different numbers. And we can see that it's been drastically reduced in size. And the reason why this is important, well, it also increases evaluation time as well. So here we do the square root of the dot product of the two arrays. In the constant array, 0.46 seconds, and in the sparse array, it is 1,000 times faster. Plotting efficiency. So this is something that a lot of people, I guess, don't think about when they construct their plots. So here we're just making a list line plot, and we're just going to show the mesh which shows the evaluation points, and we just set the image size. So what we can see is we can see all these points where all the points creating the curve are shown, and we can see that the size is 5,000 bytes. But what happens if we change the maximum number of plot points to 25? We can see it's been reduced. Well, we can see the quality is reduced as well, but it has reduced the size of the plot. Now, obviously, in this case, we're only looking at, well, like 50 points in the first place, so it's not such a big deal. But let's say we have, we have a list line plot with 1 million with 1,000,000 points, and then we try and do a list line plot on that. Well, we'll run it. We'll see if it finishes by the end of the talk. Okay, it wasn't too bad, but as you can see here, there's 16 million. Now, if I set the maximum plot points to 500, it's a lot faster and it's drastically reduced in size. So this is really important. And what you can see is also when I try and expand this, I think this is a good demonstration, I suppose, not particularly scientific, I suppose, but you can see that it's quite hard to move around because there's 1,000,000 plot points in there, but in this case, it's a lot faster. So not scientific as such, but it's important to know that when it's bigger, it's going to be harder to do any resizing or moving around. So the great thing about Mathematica is it's actually very good at doing things like this for you. So here we've got some plot, and we're just showing the mesh again and seeing how big the byte count is. And here it's 35,000. Now here we're going to change up some of the parameters. So we're going to change the plot points to 150. Max recursion to 0, and what max recursion means is the number of recursive subdivisions which can be made. So we'll find out the byte count, 22 million, but now we'll change the max recursion to 10 with the plot points to 10, or the max recursion shouldn't be that high actually, it should be 0, I guess. And what we can see is we've changed the plot points and it's reduced it drastically, and also if we change the number of recursions as well, then we reduce the size drastically as well. So another thing to be aware of is what happens when you operate dynamics. So Mathematica generally does a good job of doing this for you, so you don't have to think about it. So we have this manipulate of this plot where we just want to change the we want to change the plot range in this case, I think. That's right. And we change it, and we can see that it's not a full diagram until we actually let go. So we have this thing where the control is active or not. And you can see it's quite fast to move around, but you can say, well, I want to know a little bit more here. When I have the controller active, I want to be able to set these parameters myself. So all that's changing really is plot points and max recursion. So control active says if the controller is active, in this case, plot points is 10 and max recursion is 1. And then when I let go of the controller, we'll have plot points is 20 and max recursion is 3. And what we can see is we end up having a more accurate manipulate if that's what we want. It is going to be a bit slower, so that's good to bear in mind. But if you want to fine-tune things yourself, you can do. Another thing you can do is just turn continuous action to false. So if you don't want to think about it at all, and it's always going to be going slowly for whatever reason, then if you turn continuous action to false on the variable change, then it will only evaluate once you've let go of the slider in this case, or the controller. And then we also have a performance goal, which we can change as well, which changes within Mathematica's internal methods of calculation, whether or not we want speed as our performance goal or quality. So here, when we let go, when the controller is active, we are interested in speed, and then when we let go of the controller, then we're interested in quality. And if we're just interested in quality, we can put performance goal to quality, and then we can move this around, and you can see it's a bit more sluggish because we said we specifically want quality. Now, I wanted to mention these additional notes on dynamics. So here we say x equals 0, and we have a dynamic where it runs x equals x plus 1. Now, and then so we're dynamically evaluating x equals x plus 1, and then we're showing x. Now, when this dynamic, so this bit here is the dynamic, when we hide it, it won't hide it away from the screen, or we hide it by closing the cell bracket structure, we'll find that it stops. So this is very important because let's say we have, well, I'll stop that now. Let's say we have this manipulate, and what we can see is it's a nice manipulate. But then if I had a second one, oops, that's quite a few. We can see that it slows down because it's dynamically evaluating all of this stuff at once, or at least whatever's on the screen. So what I can do is I can start hiding these. And now it's back to normal. So we'll only evaluate when it's on the screen. Okay. So some additional memory-related functions that we've got here. Well, one of the things you can do is clear the cache. So clear system cache does this. So what this means is, let's say we run this, we want pi to 10 to the 5 places. How long does it take? It takes 0.05 seconds. Now, when we run this again, it will be faster because the answer has been cached or cached. And we can see that when we run it again, it's a lot faster. So it probably doesn't actually take up too much memory, but just to show you, the memory is 48 million here. We clear the system cache. And then it's reduced by a small amount, but as the cache builds up, it may have an impact on your performance. I don't think it does really, but as soon as you clear the system cache, we'll run this function again, and we can see it's taking the same amount of time as it had done previously. So it's good to know these things. So another couple of functions which you may find interesting. Time used tells you how much CPU time has been used in a given session. Max memory used is the maximum memory used in a given session. A useful one is memory constrained. So we can say we only run a calculation based on the amount of memory it takes. So if it exceeds, in this case, 10,000 bytes, it will return $aborted. If it doesn't succeed, in this case, we have some do loop, and we say we're using time constrained, and time constrained is the same as memory constrained, but of course it's relating to time. So it'll try and evaluate in 0.5 seconds, and if it doesn't, then it will abort. So what you could do as an example is we could have some plot, this plot before, which has a list line plot with 1,000,000 points, and we can say, right, if the memory use increases over 100 million, then we basically run a smaller one, the smaller one being max points equals 500. What we'll see is with this, well, it exceeded over 1,000,000, and now it's gone for the fast version. So that's good to know. Now, dump save is something which is really, really useful, and it's not quite related to memory efficiency, I suppose, or you could see it in some way. And what dump save does is allow you to save definitions of any symbols you like, basically. So here I've got x equals 2, y equals 6, z equals 7, and a equals this plot. Now I can do a information to get the information on anything that's in the global context. So all of these values are in the global context. It returns x, y, z, a. And I don't think I need that actually. Well, okay, I'll take that as well. So I've got these outputs as well. I'll set the directory to a temporary directory, and I can use dump save to save certain symbols. So I could define the symbols a, x, y, z, or if I want to save the complete state of my kernel, I can basically use global backtick, and it will save anything in the global context. I can save the outputs, and I can save the inputs. So we'll just have a look at this. So now we've saved to f.mx in this temporary file some values. We'll quit the kernel. We'll run global backtick question mark and x equals 2 in this case because of this isn't actually a good example. Let's say x equals 10 because this will show you something else which is useful. So I'll quit the kernel again. And the only symbol was the symbol that I initialized with. It says x equals 10. And now I can set directory again to this temporary directory, and I can import this MX file. So an MX file is like a .m file, but it's a binary file, so it's a lot faster to load. So now I'll load it up. And now I can find out what x is, and x is 2, because when you load up your MX file, it overrides all symbols that you previously defined that have any matches. So in this case, I defined x equals 10, and now I've overridden x. So we're basically saving the complete state. So now I can go to this question mark backtick star again, and it's returned all my symbols. And I can look at the down values, and apparently it hasn't saved any of them. So that didn't work as planned. I'm not sure why, but I'll move on. So another thing to bear in mind is you can expand memory usage. So this isn't quite saying memory efficiency, I suppose, but to speed up calculations and stuff like that, you can use launch kernels to launch all of your kernels. So most people, I suppose, will have 4 as standard. And why this is important? Well, we can do parallelization in this case. So here we're going to get all the Mersenne, I still don't know how to pronounce this, primes over the range of 1,000 to 3,000, and we say, okay, what we do is we do 2 to the power of a number minus 1, is it a prime number? And that's what Mersenne prime is. Now, if we do it on one core, we'll find out how long it takes. It takes 2.4 seconds, and it's return the primes. Now, if we parallelize this expression just by wrapping parallelize around it, we'll see it's a bit faster. It's twice as fast, which is quite nice. But one thing to bear in mind is that this is the same thing I said in the training course on Monday for those of you who were there, that all expressions get split across. So here we're doing a map over 10 values, and we're pausing every second. So what you would expect, if you're pausing 10 times, it would take 10 seconds. But as soon as you parallelize, you're splitting over multiple cores. And what that means is that it's going to, well, in this case, we're splitting over 4 cores. So in theory, it should be four times faster or similar to 4 times faster. So instead of taking 10 seconds, it's taken 3 seconds. And just so you know, it's not you shouldn't always just parallelize at will, because it doesn't just whenever you feel like it, because it may not always work. So in this case, we do a transpose of a 500 by 100 by 100 grid. And we can say if we just use map, it takes 0.065 seconds. But if we use parallel map, which is a parallelization function for map, it takes 1 second. So that's actually 20 times faster. Reap and sow is another thing which is a good thing to know about, because this helps increase memory efficiency. So basically, let's say we have a list, and then we want to append to a list, and in this case, we're going to be using a do loop. We append to the list a number, a random real number 40,000 times. How long does this take? Well, I think it takes, okay, that's faster than I expected, but 3 seconds is still 3.7 seconds is still quite slow. What is happening here is you get a list, you add a number to it, you add a number to it where you create a new list and then add a number to it. So what happens with append to is you're always creating a new list every single time you're appending to a list. So what you can do is use reap and sow, and what sow does is sow collects all the data, stores it until the evaluation is complete. So here we're saying store this random real 40,000 times in this do loop, and at the end we want to reap all that data and combine it into a single list. And in this case, it takes 0.09 seconds, which is I don't know how much that is, 40 times faster or something like that. Okay. So this is something which I don't think, well, is this something that I think you should be aware of, just so you know this can actually speed up your processing time quite drastically. So here we arrive, where have I put this? Is this going to work? Yes. So here I am going to set the directory to my notebook directory, and I have this data which I downloaded off the internet on information on airports It's a 9 megabyte file, and basically I want to read a record of it first, just to see what the data looks like. And the first row is the information here. And basically what I want to do is I want to take the latitude and longitude of this data. So we can read through this data one line at a time, basically. So now when we read this data one line at a time, we want to write it to another file. So just so you can see, we can use the function write to write data to write to this text file that I've just opened, and record through this data 100 times, basically. So now when I import this data, I've taken the first 100 rows of the file I've just created. And I can even append if I want to. So if I want to split this calculation up into sections for whatever reason, I can save the state and then open up my text file again and then add some more values. In this case, I'm going to add 10,000 more values. And I have to close it. And then I can open it again. So here I'm just going to use system. No, that's my fault, I think. And that's because, what have I done wrong? Because it's probably here. Yeah, so here's my 10,000 rows that I've just written. So I'm just extracting the information. But obviously I'm just doing this into a text file right now. I'll reset the position, clear some values. And what I'll do now is I'll use reap and sow to get the 5th and 6th values, so these longitude and latitude values for the whole of the 9 megabyte file. And how long does this take? It takes 2 seconds. The memory used is 273 million, but that's not too important to understand right now. And what I'll do is I'll use import, so the import function that we have, to do the same thing. And when we use import to do the same thing, we'll find that it's slower. So in this case, we've basically achieved the same thing as above, but what's ended up happening is ended up being I don't know, 30% slower to do this. And this is actually a small file, so this is a 9 megabyte file. But you can see if you're doing it with a gigabyte file or something like that, you will want to read in one row at a time. Otherwise, you're going to have a serious problem when you try and import it all in one go. And in this case, you know, this is a small file, and we're already seeing a significant slowdown in doing this. So this is why you should be careful when you use import, because import has to read in all the data and then has to reformat it for you based on the text, the file that you're importing, and this can end up using more memory. So you should always try and compile lower level code. So in this case, we do some function. Doesn't really matter what the function is, but we'll run the function 200 times, I think. Yeah, that's 200 times. We'll see how long it takes. This is the one that takes 9.6 seconds. I try and be clever, but I think my machine. I installed a new update, and I think it's ended up being a bit faster actually. So if we can define a function like this. If we just put compile around it, instead of write function, we write compile. This makes a compiled function, and we do the same thing as we did before. It is how much faster is that? 40 times faster. What we can also do is we can actually put parallelization to true, so it automatically parallelizes those over multiple cores. How long does that take? So we put it to listable attribute and parallelization to true. How long does that take? That is another 3 times faster. And what we can do, depending on your target machine and stuff like that, in this case, if you have a C compiler, you can generate a DLL for your compiled function. So it runs directly onto the CPU instead of running through the Mathematica virtual machine. We run this, and it's now 10 times faster than the previous one. So we end up having a speed up of over 100 times. And just so you know, probably not too much time to talk about it now, there's also this function internal bag. So what you can is basically reap and sow within compile. So this is something you can look at. I'll put these notes available for you to download yourself anyway. And basically what you can do is reap and sow within a compiled function, because higher level functions do not work with compile. You can't just compile everything, because you are going to be, well, compiling essentially to C. So you should also prevent unnecessary computations. So let's have a look at some attributes of functions. So square root has certain attributes here. One of them is listable, one of them is a numeric function, and one of them is protected. But there's something that's quite important for different functions. So if we have a look at plot, I think we can go attributes, plot. Okay, that doesn't show it actually. But what is known is that plot has a hold all attribute, which basically means that it always holds the evaluation of a function until it goes through all the values. So here we do some integral between x and n, and we go from in the plot 1 to 15, and we end up having this issue where it ends up being a lot slower, because each time it goes n equals 1, let's do an integrate. N equals 1.01 or something like that, do the integrate. 1.02, do the integrate. Again, over and over and over and over. And what we'll find is to do this plot, it takes 10, 11 seconds, because we're not mapping integrate. We are doing them all separately in order. Whereas map can split across multiple cores sometimes and automatically, and do some other wondrous stuff to speed up computation. But what you can do is you can just wrap evaluate over this function, and it will automatically evaluate the holded whatever's held in between. So we do the same thing again. We run it, and we'll see that we've almost got a 10 times speed up just because we wrapped evaluate. Another trick that you can do is use with to do the same thing. So with actually is a function which is quite special in the fact that you don't have to worry about the hold function there. If anything is being held, it will evaluate first, and it does a very similar thing. And in this case, it will be about the same speed as if you used evaluate. Oh, I've actually ended up going quite fast, but if I've got 5 minutes left. This is actually the last slide. So, okay, that will give some nice time for questions, I guess. So let's have a look at a graphic. So we have this graphic, and it just puts a point on top of a graphic, a red point on top of the graphic. Let's say we wanted to manipulate where that point actually was. So we can use manipulate to do this. And now when we move this value, we can see that it's being really, really, really slow. And the reason for this is because we're basically evaluating the whole graphic again and again and again, because we haven't specified what specifically changes within the graphic. This may be a little bit difficult to understand, I suppose. But what we can see is the point here is this red point. If we just wrap dynamic around it, we're telling Mathematica this is what is changing when this is the only thing which is changing in the graphic. Because what a graphic is just a bunch of objects all on top of each other and stuff like that. And what that means is if you only want to change one of those objects, if you wrap dynamic around it, then you're specifically saying, I only want to change this object. And in this case, I'll run it now, and we'll have a significant speed up.